We now introduce the discrete memoryless channel. A discrete channel can be used repeatedly at every time index I equals 1, 2, so on and so forth. Assume the noise for the transmission over the channel at different time indices are independent of each other. To properly formulate a DMC, we regard it as a subsystem of a discrete time stochastic system, which will be referred to as the system. In such a system, random variables are generated sequentially in discrete time. More than one random variable may be generated instantaneously, but sequentially at a particular time index. We now introduce our first definition of a DMC, called DMC1. This definition is based on our first definition of a discrete channel. A DMC specified by a transition matrix Py given X is a sequence of replicates of a generic discrete channel Py given X. Let Ti minus be all the random variables in the system generated before Xi, the input to the channel at time I. The memoryless property of the channel, which corresponds to the independent noise assumption, is specified as follows. The probability that Yi, the output of the channel at time I, equals small I, and Xi, the input to the channel at time I, equals small x, and Ti minus 1 equals some value t, is equal to the probability that Xi is equal to x and Ti minus is equal to t times Py given X. Note that the transition probability Py given X here corresponds to the probability that Yi is equal to small I, given Xi is equal to small x, and Ti minus is equal to t. As such, the memoryless property is actually equivalent to the Markov chain Ti minus Xi Yi, or, in words, given Xi, the input at time I, Yi, the output at time I, is independent of everything in the past. Definition 7.4 is the formal definition for DMC1. A discrete memoryless channel, Py given X, is a sequence of replicas of a generic discrete channel Py given X. These discrete channels are indexed by a discrete time index I, where I is greater than or equal to 1, with the ith channel being available for transmission at time I. Transmission through a channel is assumed to be instantaneous. Let Xi and Yi be respectively the input and the output of the DMC at time I, and let Ti minus denote all the random variables that are generated in the system before Xi. The following equality holds for all x, y, and t. The probability that Yi is equal to small y, Xi is equal to small x, and Ti minus is equal to small t is equal to the probability that Xi is equal to small x, Ti minus is equal to small t times Py given X. We now introduce an alternative definition of a DMC called DMC2. This definition is based on our second definition of a discrete channel. A DMC specified by the pair alpha z is a sequence of replicates of a generic discrete channel alpha z. Zi is the noise variable for transmission at time I and has the same distribution as z. The memoryless property, which corresponds to independent noise, is specified as follows. Zi, the noise variable for the ith transmission, is independent of xi, the input at time I, and ti minus, all the random variables generated in the system before xi. That is, the noise for transmission at time I is independent of both xi and everything in the past. Definition 7.5 is the formal definition of DMC2. A discrete memoryless channel alpha Z is a sequence of replicas of a generic discrete channel alpha Z. These discrete channels are indexed by a discrete time index I, where I is greater than or equal to 1, with the ith channel being available for transmission at time I. Transmission through a channel is assumed to be instantaneous. Let xi and yi be respectively the input and output of the DMC at time I, and let ti minus denote all the random variables that are generated in the system before xi. The noise variable zi for the transmission at time I is a copy of the generic noise variable z and is independent of xi and ti minus. The output of the DMC at time I is given by yi equals alpha of xi, zi. The equivalence of definitions 7.4, namely DMC1, and 7.5, namely DMC2, can be shown. For details, please see the textbook. For the rest of our discussion, assume that both the alphabet x and the alphabet y are finite. Definition 7.6 defines the capacity of a DMC. The capacity of a discrete memoryless channel, Py given x, is defined as C equals the maximum of the mutual information between x and y, where x and y are respectively the input and the output of the generic discrete channel, and the maximum is taken over all input distributions Px. The meaning of this maximization is explained as follows. For each input distribution Px, we can determine the joint distribution of the input and the output of the channel as Pxy equals Px times Py given x, because Py given x is given. From the joint distribution Pxy, we can compute the mutual information between the input and the output of the channel. Then maximize the mutual information between x and y over all input distributions Px. Here are a couple of remarks. Since Ixy is a continuous function of Px, that is, Ixy varies continuously with the input distribution Px, and the set of all Px is a compact set, that is, it is closed and bounded in the Euclidean space with dimension equal to the size of the input alphabet x. The maximum value of Ixy can be attained. We are going to see that C is in fact the maximum rate at which information can be communicated reliably through a DMC. So indeed, it is possible to communicate through a channel at a positive rate while PE, the error probability, tends to 0. In example 7.7, we look at an alternative representation of a BSC with crossover probability epsilon. The output variable y is equal to the input variable x plus a noise variable z, where the addition is in modulo 2, with the probability that z is equal to 0 being 1 minus epsilon, and the probability that z is equal to 1 being epsilon, and z is independent of x. Note that when z is equal to 0, y is equal to x, and when z is equal to 1, y is not equal to x. Therefore, y is not equal to x with probability equal to epsilon. So this is exactly the same model of a BSC that we have seen before. We now determine the capacity of this channel. First, consider Ixy, the mutual information between the input and the output, equals hy minus hy given x. We then write hy given x as summation small x, p small x, h of y given x equals small x. Now the conditional entropy of y given x equals small x is equal to hb epsilon, which does not depend on x. Therefore, we can move it outside the summation, where summation xpx is equal to 1. Now this is less than or equal to 1 minus hb epsilon, because y, being a binary random variable, has entropy at most equal to 1. So, the capacity of the channel, which is equal to the maximum of Ixy over all input distribution Px, is less than or equal to 1 minus hb of epsilon. Now the upper bound on Ixy is tight if hy is equal to 1. It can be shown that by taking the input distribution to be the uniform distribution, the output distribution is also the uniform distribution, and so the entropy of y is equal to 1. Therefore, we conclude that the capacity of the channel is equal to 1 minus hb of epsilon bit per use. This is the plot of the channel capacity versus epsilon, the crossover probability. When epsilon is equal to 0, C is equal to 1. Intuitively, this is correct because there's no error in the channel, and so we can communicate information at the rate 1 bit per channel use without error. When epsilon is equal to 1, that is, there's always an error in the channel, C is also equal to 1. Again, intuitively this is correct, because for such a situation, the decoder only needs to flip the value of y in order to recover the value of x. Therefore, from the information transmission point of view, there is no difference between epsilon equals 0 and epsilon equals 1. When epsilon is equal to 0.5, C is equal to 0. It can be shown that the input x and the output y are always independent when epsilon is equal to 0.5. We leave the proof as an exercise. For this reason, by knowing the output y of the channel, nothing is known about the input x of the channel, and so it is not possible to communicate any information through. Therefore, intuitively, the channel capacity is equal to 0 when epsilon is equal to 0.5. We now introduce the second channel model, called the binary erasure channel. The channel description is the following. The input x to the channel is binary, while the output y of the channel can take value 0, 1, and e, where the output symbol e denotes erasure. Gamma is the parameter of the channel called the erasure probability, where gamma is between 0 and 1. With probability equal to 1 minus gamma, the output is equal to the input, regardless of the input being 0 or 1. With probability gamma, y is equal to e, the output is equal to the erasure symbol e. If x is equal to 0, then y cannot be equal to 1, and if x is equal to 1, then y cannot be equal to 0. In other words, in the binary erasure channel, either there's no error or there is an erasure. The erasure symbol can be interpreted as follows. In some communication systems, a symbol transmitted into the channel can be lost, and so it is not received by the receiver. In other communication systems, the receiver may not be able to distinguish between 0 and 1. In both situations, it can be modeled as an erasure. We now determine the capacity of this channel. First, consider the channel capacity C equals the maximum of IXY, the mutual information between the input and the output, over all input distributions Px. Now IXY is equal to HY minus HY given X. And HY given X is equal to HB of gamma, which is evident in the transition diagram above. Since HB of gamma does not depend on the input distribution Px, we only have to maximize HY over all Px. Toward this end, we let P0 equal to A. This is indicated in the diagram. And we also have P1 equals 1 minus A. We are going to find the value of A that maximizes the output entropy H of Y. Now we define a binary random variable E by E equals 0 if Y is not equal to E, and E equals 1 if Y equals E. The random variable E indicates whether an erasure has occurred, and it is a function of Y. Therefore, HY is equal to HY and E because E is a function of Y. This is equal to HE plus HY given E. Now HE is simply equal to HB of gamma. It can be shown that HY given E is equal to 1 minus gamma times HB of A. We leave the proof as an exercise. Following from the above, we have C equals the maximum of HY over all Px minus HB of gamma. Using this expression for HY, the maximization is equivalent to HB of gamma plus 1 minus gamma times HB of A, where the maximization is over all A between 0 and 1. Now this HB of gamma cancels with this HB of gamma. And therefore we are left with 1 minus gamma times the maximum of HB of A over all A. This is equal to 1 minus gamma because the maximum of HB of A is attained when A is equal to 0.5. That is, when the input distribution is uniform. Therefore, we conclude that the channel capacity is equal to 1 minus gamma bit per use.